Good morning, student. So, in today's lab session, let's see what happens when a single phase half wave controlled rectifier is given with an RLE load. So, last class we have seen about an R load. So, here it will be an RLE load. So, the EMF, that is we either use the battery or something for the DC voltage. Okay. Then it will be the inductance and then will be the R. So, this much will be the load side. Okay. So this much will be the load side, and we have the input, that is Vm sine omega t and and we have the thyristor here, that is we are using as the switch. Okay, and then this is the output current. So now let's see what happens in case of a RLE load. So we know that there will be the input will be sinusoidal. As always, the input will be sinusoidal input. So this is 0, this is pi, and this is 2 pi. And we can also draw the DC voltage also we should draw here. So the DC voltage will be E. Okay, the DC voltage is E. So this is E. This is the omega t axis here. And here we can see that, just change the color. Here we can see that from 0 to some angle theta 1, let's call it theta 1, from 0 to some angle theta 1, the voltage source, the input voltage source Vs is less than the output E. That is from 0 to theta 1, Vs happens to be less than the EMF E. Sorry, the DC voltage source E, right? Here it is less than. In that case, the output voltage will be E itself, because the thyristor is reverse biased here. The SCR is reverse biased. So in this condition, the SCR is reverse biased. So output voltage V output is equal to only E. The output voltage will be only E. So this is the output. So the output voltage will be only E. Up to here, the output voltage will be only E. Then at 90 degree, that is at omega t is equal to 90 degree, we give the firing pulse, that is alpha, the firing angle is equal to 90 degree. That means the thyristor gets on there, right? The thyristor will be on at alpha is equal to 90 degree. So we are giving the gate pulse. So we are giving the gate pulse here. Similarly, here also we'll give the corresponding gate pulse. This is the source voltage Vs and this is the gate current Ig. The gate current Ig. So here we can see that up to the firing angle we will get 90 degree, and then from here we will start getting the source voltage. So this will go like this and this will be pi, right? This will be pi and this will go like this, and at pi up to here we will get the output voltage, and here again the condition is reversed, but we will get a negative voltage due to the presence of the inductor. We will get a negative voltage due to the presence of inductor, and this angle we normally call as beta. Okay, so here we get a negative angle which is called beta, and then that is from theta 2 to pi, that is up to theta 2. This is the angle theta 2. Then from theta 2 to pi also, Vs is less than E. So that's why we find the angle between. So alpha should be between should be between theta 1 and theta 2. So alpha should be between theta 1 and theta 2. So we give alpha is equal to 90 degree. Okay, and due to the presence of inductance, there will be a negative voltage which appears across the load. So then the same procedure repeats. So here it will be there. Then we will have the firing angle. Again, it will come. Same way it will go. Okay. Now let's talk about the output voltage, output current. Sorry. So we can see that the output current and the source current will be same here because they are in series. So you get the output current when the SCR is on only. No? When this part is conducting, we get the output current. So we can say it like here we will have the output current. Here SCR is on. Then again here the SCR is on. So the output current. So when the SCR is off, we will have the voltage across the thyristor. That also we can plot. So this is the concept of single phase half wave control rectifier. Just summarize. So voltage source and the load will be RLE, sinusoidal voltage source, and then there will be a DC voltage source in the output. So initially when the SCR is off, the output voltage will only be E. Okay, this is E. The output voltage will only be E, and when after passing the angle theta, that is the case when the source voltage is less than E, that is when we actually get it forward biased. After getting the SCR forward bias, that is when it conducts, we give the firing angle. So we know we get the output only after we give the firing angle. So here we give 90 degree. So accordingly, we got the firing angle. So it should be between theta 1 and theta 1 and theta 2. That's actually condition is the source voltage should be greater than the output voltage E. Okay, that's only when SCR get forward bias, or else SCR will be reverse bias. Now let's see how to implement this in a MATLAB simulating environment. So this is the MATLAB environment. So I have already done everything, the input voltage source, then RLE. So RL I have given like 10 ohm resistance and 10 millihenry. And then the DC voltage we have given 100 volt. So all these things you can see, you can identify in the output when you take. That's why I explained you the theory in the beginning. And the phase delay is 90 into 0.0. So 0.02 for 20 millisecond by 360. The same way you did the R load. And I have given the time duration for simulation is 0.04 just for the easiness. Okay, I will simulate it. So the simulation is completed. Then let's go to the scope, and that's what you get. The input voltage source, so 230 volt I have given. Then the gate pulse, which was given at 90 degree. So only when we get the gate pulse at 90 degree, we are getting the output. And then at pi, after that, there is a small voltage source. There is a negative voltage due to the inductance L. So depending upon the value of the inductance, this value you can get how much you want. So if I have given 10 millihenries, that's why we get a small value. If you give more means you will get more. And then this is 100 volt. You remember 100 volt is the output DC voltage. That's how we get it. Same way which we have derived, we are getting in the MATLAB simulation also. See here also you can see that it's this is the output output current. Same way we have got it. Hope you understand. Thank you.